So in this class, I will explain about another concept which is very much useful in the analysis and design of structural members: deflection of beams. So you know different types of beams: simple supported beam, cantilever beam, overhanging beam, fixed beam, continuous beam, like that, proper cantilever, etc. When a beam, here I have considered a simply supported beam. A and B are the simple supports on which a UDL and point rods are acting. So due to the application of those external forces which are called as actions, reactions will develop at the supports. So these things you have learned in your mechanics. You know how to find the reactions also using the equations of equilibrium. Now due to the effect of this external forces on the beam is to shift this axis. So this is the imaginary line which is called as the axis of beam. So due to the application of these external forces, so the axis of the beam gets shifted like this. So this curve is called as the elastic curve or the deflected curve. That means it is shifted. So here at the support you can see it is not shifted because the reaction resists the shifting. So here, due to this development of this elastic curve, you can see that if you draw a tangent at A here to this curve, there will be an angle here, theta A. Theta A is the angle. Similarly, if you draw a tangent to this curve at B, it makes an angle theta B with the axis of the beam. So this theta A and theta B, they are called as the slope or rotation. So it can be either clockwise or anti-clockwise. Similarly, you have at C and D. At C and D, these 2 points, this axis this point gets shifted over here. So this vertical shifting or in the transverse direction is known as the deflection. So here, since it is at C, it is denoted by YC. So Y we are going to use for deflection. So here at D also you will be having a deflection, that is YD. So in this chapter we are going to find out these slopes and deflections of different beams when subjected to different types of loadings. Now here at some point you can see here at some point you have, if you draw the tangent, it will be parallel to this axis of the beam. That means the value of theta will be 0 here at some point. So the tangent will be parallel to the axis of the beam. So at that point, let me take that point as E here. At that point, you can see that maximum deflection will be there, like this. So this is how it deflects. So at some point here, you have the theta value 0. If you draw a tangent, it will be parallel to this axis. And therefore, at this point, you can say Y is maximum. So the one important thing is, at the point where the slope is 0 or rotation is 0, we can expect the value of maximum deflection. Now, to find out the slopes and deflections, we have to use certain conditions called boundary conditions. Boundary conditions are known conditions, known geometrical conditions. So here, 3 important boundary conditions we can have. So one thing is, at simple support, suppose if the support is simple support, deflection will be 0 on the simple support, whereas slope is not 0. You can see here, A is a simple support, YA is 0 here, there is no deflection here because the reaction resists the deflection, whereas this rotation will be there. Similarly at B, YB is 0, but the theta B is not 0, it exists. On the other hand, if it is a fixed support, just in the case of a cantilever beam or a fixed beam, so you have both deflection and slope 0 at the fixed support. For example, if you have a cantilever like this, it is subjected to some loading like this. Let us say the deflected shape of this axis will be something like this. So here at this A, so both theta 0 and deflection is also 0. So at the fixed end, you don't have any rotation, you don't have any deflection. Whereas at the free end, so this is B is the free end here, you have both rotation as well as deflection. If you draw a tangent here, so the tangent makes an angle with the axis, so that is theta B. So both theta B and YB exist, whereas theta A and YA they will be 0 here. That is the second boundary condition. Now the third one is, suppose if it is a free end, like this here B is a free end, there is no support there. So both deflection and slope exist there, they are not zero. So and also next thing is, this is the fourth condition is, as I already told here, at the point of zero slope. That means when theta is 0, deflection is maximum. So y is maximum. So that is the meaning. So y max will be there where theta is 0. So that means if theta is equal to 0, y is equal to y max. So in any being, if this condition exists, so if theta is 0, then y will be y max. Mainly in the case of simple supported beam, this condition we can use. So these are called as the boundary conditions. Now, to find the deflection, so let me initially I will consider a simply supported beam subjected to UDL. Then we will do some problems on that. Like that we can do for simply supported with concentrated load, cantilever with UDL, cantilever with concentrated load, like that. So anyway, I will discuss one case here. Let me take a simply supported beam. With UDL throughout. With UDL throughout means for the entire span. That is UDL. So let me write the diagram for that. So I will take the simple supported beam like this. This is simple supported beam. I will take the UDL. So this UDL intensity I will take it as W per unit length, and let me take L is the span. L is the span. So you can observe here that if I take C as the midpoint or the midspan point, L by 2, if you see the beam, it is symmetrical. So the beam is completely symmetrical. Therefore, the deflected shape curve also will be symmetrical. So if the deflected shape in this case, it will be like this. We can observe that maximum deflection occurs at C here. So this is very important. YC is Y max. So in this case, YC is equal to Y max. And if you draw the tangent here at A to this curve, this elastic curve, the angle made by the tangent is theta A. If you draw the tangent here at B, the angle is theta B. Since the symmetrical beam, theta A will be equal to theta B. The only thing is this theta A is clockwise, where theta B is anti-clockwise. So magnitude wise, they will be equal. So normally this deflection is expressed in millimeters, whereas slope is expressed in radian. So you know the radian is written like this. 1 radian is 180 by 5 degrees. So this is the conversion. So you should be knowing this. So rotation is expressed in radian, whereas deflection is expressed in millimeters. Now here, another thing is this deflection is directly proportional to span. You can see here deflection increases with span and load. One important thing. Then deflection decreases with Young's modulus value of the material of the beam and moment of inertia of the section of the beam. So it decreases with E and I and increases with span and load. We can prove that later. So once I derive the expression for slope and deflection for a simply supported beam case with UDL, so you can come to conclusion that you can verify these two points there. Now let me see how we can do this problem. Now what I am doing here is I want to find out the slope at A and the maximum deflection, that is YC. So please note that in the case of symmetrical beam, always deflection is maximum at the midspan point. So here you can take YC as Y max, and in this we can see that if you draw a tangent at C, its slope will be 0. So that is the condition. Okay, if you draw a tangent here, so this theta C will be 0. That is the condition. You can see here. At the point of 0 slope, deflection is maximum. Now, we have to use one important method called Mechanis method. I am going to use Mechanis method, or for this case, I can use double integration method also. For doing numerical examples, we will go for Mechanis method. Now, I will go for double integration method. So, this is called as double integration method. So, for using this double integration method, we have to use an important deflection equation called Euler's equation. Euler's deflection equation. Euler's Bernoulli equation, deflection equation. Okay. So it states, it can be proved actually. It states that bending moment at any bending moment at any section in a beam, which I will call as mx. It will be section. Section means that xx is the section. Bending moment is denoted by mx. It is given by ei into d square by dx square. So this is called the Euler's equation. So we have to use this for solving problems on deflection and slope. So ei, this e into I, product of Young's modulus and moment of inertia of the section. Young's modulus is a material property. Moment of inertia I is a section property. So this is called as flexural rigidity. Flexural rigidity. So if this Young's modulus is expressed in Newton per mm square, I is expressed in millimeter power 4, then this unit will be Newton millimeter square, or normally we take Newton meter square as the unit of EI. Now, what we are going to do here is, we are going to use this equation, mx is equal to ei into d square by dx square. I will, to get the slope, so this theta can also be written as dy by dx. From the calculus, differential calculus, slope can be defined as dy by dx. So please note that this deflection curve is y is equal to f of x. This is the deflection curve. If you differentiate this y with respect to x, definitely you are going to get the slope. That is the meaning. So this is the slope theta. You are going to get that. So y is the deflection, x is the axis of. So with reference to some reference point, x is 0 here, you can measure the value of x, and this is the profile or the envelope. So if you draw the tangent at any point here, the angle gives the value of dy by dx, that is theta value. That is the meaning of that. Mathematically, so theta is dy by dx. So if I take that equation, m is equal to ei into d square by dx square, or mx is equal to this much. So normally you will be knowing the expression for mx. Expression for mx you can write by knowing the beam and the loading and all, bending moment expression at any section xx, where the deflection of slope is required. At that section x you can write the expression for bending moment. So once you integrate this, so what I will do here is ei into dy by dx. So if you integrate once both sides, integrate with respect to x both sides, you will get ei into dy by dx here. This side it will be integral mx dx plus some constant c1. So please, this is very important. Constant of integration we have to add. Next, once again we integrate. Integrate once again with respect to x. So if you integrate once again with respect to x, you are going to get ei into y. Integration of dy by dx is y. Double integral. So once again I am integrating this mx dx plus c1x plus c2. Please note that one more constant of integration will be added. So here these constants of integration c1 and c2, they are the constants of integration. So these two are evaluated using boundary conditions. So we have to use these boundary conditions. I have written here, some of these. So we need two boundary conditions to get the two unknowns constants C1 and C2. So these two are found out using the boundary conditions. Depending on the type of the beam, type of the problem, we have to use the boundary conditions. Here, this first equation is the moment equation. Second equation is the slope equation, because it involves dy by dx, or it is nothing but theta. So this is called as the slope equation. The third equation is the deflection equation. Y is the deflection. This is deflection equation. So from the moment equation, if you integrate, you are going to get the slope equation. Slope equation, if you are going to integrate, you are going to get the deflection equation. This is the general procedure to find the slope and deflection by knowing bending moment. Now we will apply this one to this case, simply supported beam subjected to UDL. Now let me see how we can find out these values of slope and deflection. So once you get the general equations, that is slope equation, deflection equation, general equation, these are the general equations, you can find out the values of slopes and deflections at any required point by just putting the value of x. Now let me continue that. Now let me take a section xx. So I will write once again the diagram. So I am taking simply supported beam with UDL. AB is the simply supported beam, A and B are the simple supports, with UDL, W per unit length. Span of the beam is L. So and flexural rigidity is E into I. So that is the meaning. Now here, as I already explained, the deflection is maximum at the midspan because it is symmetrically loaded beam. So this is YC. So this YC will be your Y max, and if you draw a tangent here at C, the tangent will be parallel to the axis of the beam. That means theta C will be 0. So this is the equation. This is the given problem. Now reactions will develop RA and RB. So these two reactions will be equal because symmetrically loaded beam. Total load on this beam is W into L. So reactions will be half of that. WL by 2, WL by 2. That is they are the reactions. Now what we have to do is, the procedure is like this. We have to consider a section XX. So because we have to write the bending moment expression. So in the case of simply supported beam, normally X is measured from the left support. So X is measured here like this. I will take a section XX here at a distance X from the left support. So please note that X is measured from the left support. A is the left support. Now our aim is to find out this deflection, this slope theta A and the slope theta B. Of course, theta A and theta B will be equal here because it is symmetrical beam, and we have to find out YC. So theta A, theta B, slopes at A and B, this is unknown. Then YC or Y max, that is unknown. So these two we will find out by writing these three equations now. Now I have taken a section XX at a distance x from the support A. Now let me write the bending moment expression at this XX. So Mx is the bending moment at XX. So this will be equal to, see to the left side of the section. So this RA will give a bending moment of WL by 2 into x. You know that the sign convention is, if you are considering left side or right side of the section, upward forces give positive bending moment, that is sagging bending moment. Downward forces give negative bending moment. All these I have explained in my lectures in the bending moment diagram and shear force diagram chapter. You can refer that. So WL by 2 into x due to this. Then due to this UDL is downward, so minus W into x is the load into it acts at the midpoint. UDL always acts at the midpoint. So x is the distance, so midpoint is at x by 2. So Wx into x by 2. So this is the bending moment expression. So we have got WL by 2 x minus Wx square by 2. So this is the bending moment expression at the section XX. So therefore, according to the Euler's So mx is equal to ei into d square y by dx square. Now therefore I can write ei into d square y by dx square is equal to mx. Mx is this w l by 2x minus w x square by 2. So this is the bending moment equation or the moment equation. We can call this as 1. So moment equation, I will take this as equation 1. Now integrate this with respect to x. Integrate with respect to x. You are going to get this slope equation. Second equation you are going to get ei into dy by dx or theta. So this dy by dx can also be written as theta is equal to, now I will integrate this with respect to x, w l by 2 into x square by 2 minus w by 2 into x cube by 3 plus c1. Don't forget to write that the constant of integration. So this, if you simplify, you get w l by 4 x square minus w by 6 x cube plus c1. So this is equation 2. So the first one is called as the moment equation. Second one is the slope equation or the rotation equation. Now once again, if you differentiate this slope equation with respect to x, you are going to get the deflection equation. So because integration of dy by dx is y itself. So now what I will do here is integrate once again with respect to x. So integrate with respect to x. It becomes ei into y now. Ei is a constant. So the integration of dy by dx is y. If you integrate the RHS term, it is w l by 4 into x cube by 3. Integration of x square is x cube by 3 minus w by 6 into x power 4 by 4 plus c1 x plus c2. So one more constant integration will be added here. So what I can write this as w l by 12 x cube minus w by 24 x power 4 plus c1x plus c2. Now this equation I have written as equation 3. This equation is called as the deflection equation. So from the moment equation, by integrating we get slope equation. From the slope equation, by integration we are going to get the deflection equation. Now next thing is to find the constants of integration. To find c1 and c2, so we have to use the boundary conditions. Now let us see what are the boundary conditions we can use in this case, because I told selection of boundary condition depends on the selection of the type of beam and the problem. Now since it is simply supported beam here, so what I do here is at the support, that means at the support A or support B, you know that deflection is 0. There is no deflection at A, that is one boundary condition. So that means x is measured from here. So that means x is 0 here. At A x is 0. So at x is equal to 0, y is equal to 0. That is the first boundary condition. So at A, that means at the simple support, x is 0, y is also 0. This is the first boundary condition because there is no deflection at the support. Now this I have to use in equation 3 because y is there in equation 3, you know. Ei into y is there. So substituting in equation 3, so LHS becomes 0 because y is 0. RHS first term will be 0 because x is 0. Second term is also 0. Third term is also 0. Fourth term is C2. So from this you get C2 is equal to 0. This is first value. Now second value is, now here since we can make use of the symmetry property, this is symmetrical beam. So the boundary condition what we can use is at the midspan point, that is at C, slope is 0, deflection is maximum. So slope is 0 at the point C. So what is the value of L at the point C? It is L by 2. Because x is measured from A to C is half of the span. So I can write at C, that is midspan. C is the midspan point, A is the support. So x is L by 2, x is equal to L by 2 and theta is equal to 0. Please note that. This is the second boundary condition. So whenever you have a symmetrical beam, you can make use of this boundary condition. So now here, if you substitute once again, substituting in once again equation 3 because y is involved in equation 2 because theta is involved here. So equation 2 is this. So this dy by dx is nothing but theta. Please note that either you can write it as dy by dx or theta. So this becomes 0 now. So theta is 0. So substitute in the equation 2, LHS becomes 0. RHS, wherever x is there, input L by 2. X is L by 2 there. So W L by 4 into L by 2 square. W L by 4 into L by 2 square like this. Okay. Minus W by 6 into L by 2 cube plus C1. So this is what we get, plus C1. Now therefore you can get C1 value from this. So C1 will be equal to this minus this. So this will be W by 6 into 8, 48 L cube minus, this becomes minus W L by 4 into 4, 16. 4 into 4, 16 into L. So that means there is also L cube. So this is what you will get. Now here C1 can written as now W L cube by 16. 48 is the LCM. Okay. You will get W L cube into 48 is the LCM. So it becomes 1 here minus 3. 1 minus 3. So that means minus 2 by, I can write this as minus 2 W L cube by 48 or minus W L cube by 24. So this is the value of C1. So once you get the values of C1 and C2, constants of integration by using the boundary conditions, now substitute them back into the equations 2 and 3 now. So if you have to substitute for C1 in equation 2 and for C1 and C2 both in equation 3 to get the general slope and deflection equations. Now let me substitute and then we will find out the slope and deflection at whatever required points. So substituting for, I will write substituting for C1 and C2 in equations 2 and 3. First let me substitute in equation 2 EI into theta. So EI into theta is equal to W L by 4 x square minus W by 6 x cube. C1 will be minus W L cube by 24. That's what I have substituted. C1 is that value. So this becomes equation 4 now. So 2 becomes 4. Next I am substituting equation 3 now. So it becomes EI into y. EI into y. So this is equation 2. This is equation 3. EI into y is equal to W L by 12 x cube. W L by 12 x cube minus W by 24 x power 4. Plus C1 means minus W L cube by 24 x plus C2 is 0. So this is equation 5. So equation 3 becomes equation 5. Now these two are the final or the general equilibrium, general slope and deflection equations. Once you get this equation, then wherever you want the slope and deflection, just go on, substitute the value of x there and get the values. Now in this case, let us find out the slope at A. Slope at A. Slope at A means it is theta A. Theta A we need. So if you want slope at A, x you have to put 0 because x is measured from A. You have to put x equal to 0 in equation 4. In equation, slope equation. That means what happens now? So here EI into theta A. Theta becomes theta A is equal to, this becomes 0. This also becomes 0. Only you get WL by 24 or theta A can be written as minus WL by 24 EI. So this EI you can bring to the RHS, it becomes divided. So this negative sign, of course, it indicates that it is clockwise. Clockwise. So you can see here. So clockwise, negative sign. Now, using the same equation, if I want slope at B, slope at B, theta B if I want, what I have to put here is x is equal to, I have to put x is equal to L here, because x is measured from A, from here to here, distance is L. Put x is equal to L, once again in same equation 4, so what we will get here is EI into theta B you will get, EI into theta B is equal to, now wherever x is there, put L there, W L by 4 into L square, minus W by 6 into L cube, minus W L cube by 24. Now if you simplify this, so this becomes W L cube into, I get W L cube as common, 1 by 4 minus 1 by 6 minus 1 by 24. So 24 is the LCM here, so W L cube into 24 is the LCM, so you get 6 minus 4 minus 1, so it becomes 1 only. So 1 by 24, that means finally it is theta B is equal to positive value of W L cube by for 24 EI only, but it is positive. So positive means anti-clockwise. See, I had told in the beginning, so these two values are numerically same. This is negative means it is clockwise rotation or slope, it is anti-clockwise rotation or slope. So it is measured from the axis in the anti-clockwise direction. So theta A will be like this, theta B will be like this. So for numerically they have the same value. So this plus and minus sign represents the direction. Now this is how we can find out the slope at A and B. Now the next thing is I need the maximum deflection. So maximum deflection occurs at C. At C the value of x is L by 2. So we have to put x is equal to L by 2 in equation 5 now. In equation 5 we have to put x is equal to L by 2 because we need the deflection. So put x is equal to L by 2, that is at C. So we will get y is equal to y max. Maximum deflection you are going to get. So very important, because in the design we are going to check the safety of the beam for maximum deflection case. So let us see what is the answer we are going to get. So substitute in equation 5. So equation 5 states this, Ei into y, so here y becomes y max now, or yc is equal to Wl by 12 into x is L by 2 cube minus W by 24 L by 2 whole to the power of 4 minus W L cube by 24 plus 0 of course last one. 24 into x is L by 2 once again. Yes. Now let us simplify this. What you will get, you will see. W L power 4 you get divided by 12 into 8, that is 96, minus W L power 4 by 24 into 16. So 24 into 16, 2 power 4 is 16. 24 into 16 is 384 minus W L power 4 by 48. 28 into 2 is 48. So I will take W L power 4 common here. 1 by 96 minus 1 by 384 minus 1 by 48. The LCM of these three is 384. So W L power 4 divided by 384 is the LCM. So 96 means it is 4 times minus 1, and this is 384 divided by 48 is 8. So minus 8. So you will be getting minus 5 W L power 4 by 384. Now if I want y max, EI should be brought to the RHS, it becomes divided by minus 5 W L power 4 divided by 384 EI. So please note that you have got negative sign here. Negative sign indicates that it is downward deflection. So negative sign indicates that deflection is downwards. That's all. That is why it is negative. So by sign convention, deflection is downward. So you can observe that here negative slope represents clockwise, positive slope value represents anti-clockwise, negative deflection value represents downward deflection, positive value of deflection represents upward deflection. Of course, in this case there is no upward deflection. So this is the expression for the maximum deflection in the case of a simply supported beam subjected to UDL. So it's a very important formula which we are going to use in the design of RCC beams also. So maximum deflection when a simply supported beam is subjected to UDL should not exceed this value. So here W is the intensity of UDL, L is the span of the beam, E is the Young's modulus of the material of the beam, I is the moment of inertia of the cross section of the beam, and the product EI is called as the flexural rigidity. Now we should be very careful about the units here. So normally in when doing problem, we will take W in newtons per meter. L will be in meters, then E will be in Newton per meter square, I will be in meter power 4. So these are the values normally. But what we do here is, if you take W in newtons per millimeter, L in millimeters, E in Newton per millimeter square, and M in millimeter power 4, the deflection value Y you are going to get in millimeters directly. Directly you are going to get in millimeters. So, but you should be very careful about units because in the given problem, loads will be in kilonewtons, span will be in meters. So, what we do here is normally we take the loads in kilonewtons, this thing only, and E value and I value will be in different units. So therefore, you should convert. Very important thing is we have to convert everything into standard units, and then we have to do the problem. Because normally this E value will be Newton per mm square. That you may have to convert it into kilonewton per meter square. So this is one thing. Another way is you can express W in kilonewton per meter, length in meters, Young's modulus in kilonewton per meter square, I value in millimeter power 4, then deflection value will be in meters. So either you can use this first set or you can use this set. So anyway, I will discuss that with the problem. So if you are using these units, your deflection finally we are going to get in meters, that you can later on convert it to millimeters by multiplying by 1000. So this is the general method of double integration method. I have explained how to find the slope at supports and the maximum deflection at midspan when a simply supported beam is subjected to UDL flow. This method can be followed for any type of beam. For example, simply supported beam with concentrated load, simply supported beam, cantilever beam with concentrated load, cantilever beam with UDL, like that. So statically determinate beams, we can find out the slopes and deflection using double integration method in this fashion. Only thing is we have to evaluate those two constants of integration which we are going to get after integration of moment equation by applying the boundary conditions. Two boundary conditions are required to find out the constants C1 and C2.